Hello everyone, my name is Sunwoo Kim from KAIST AI. Today, I would like to introduce our research on generative pre-training for neural architecture encoding. We start with the research background and goal. Deep learning architectures offer diverse design choices, each of which can affect task performance. Below, we consider the two choices for a computer vision model. The left model can outperform the right one in object detection, while the opposite may happen in semantic segmentation. However, identifying the performance of an architecture with actual training and inference causes huge cost in practice. To overcome this issue, people use machine learning models to predict the performance of an architecture. To this end, neural architecture encoders are commonly used to transform architectures into vector representations, which are then fed into an MLP for final performance prediction. Then, how can we train a neural architecture encoder to capture the key characteristic of a given architecture? Specifically, what are the key characteristics of neural architectures and how can we train an encoder to capture them? Let me introduce our proposed method. We consider information flow as the architecture's key characteristics. Information flow is a concept that indicates how the information flows within a neural architecture at forward pass and backpropagation. Consider the below example. At the forward pass phase, the input image is being inserted into the architecture and flows from the left to the right. Once it reaches at the output operation, it passes to the next block. In the backpropagation phase, this process is being reversed. The gradient flows from the right side to the left side. Once it reaches the input operation, the process is being completed. This process is an example of information flow. To let an encoder to learn this, we use generative pre-training. That is, we train an encoder to generate the flow representation of a neural architecture to capture the information flow of the architecture. Then, how can we obtain the representation of information flow? To this end, we propose flow surrogate, a vector representation of an architecture's information flow. Flow surrogate is obtained by a sequential message passing within an architecture, which imitates the architecture's forward pass and backpropagation. Consider the below example. We prepare initial flow representation and each operation's representation. Then, the initial flow representation propagates in the forward pass direction. It reaches 3x3 convolution and being transformed into a new representation with our transformation function whose detail is in our paper. It then moves on to the next max blue operation, perform the same transformation process, and the same process is done at the output node as well. Once the forward pass imitation is done, we perform the backpropagation imitation, which is analogous to the forward pass process except for the direction. When the flow representation reaches at the input node, it becomes the flow surrogate of this corresponding architecture. Note that all the components within the process are fixed. We now introduce our flow generative pre-training called FGP. FGP pre-trains an encoder to generate a flow surrogate for a given architecture. Here, an architecture is being fed into the encoder and decoder, then become the flow surrogate. The L2 distance is being computed between the generated and ground truth flow surrogates, and based on these laws, parameters of encoder and decoder are updated. Once the pre-training is completed, we fine-tune the pre-trained encoder for performance prediction. We obtain predicted performance for each architecture by using the encoder and MLP regressor. Then, we update the model parameters by using the margin ranking laws between the two architectures. We move on to the experiments. We evaluate our method in the performance prediction tests. To this end, we use 3 neural architecture search benchmark datasets and baseline pre-training methods for neural architecture encoding. We use 3 different backbone encoders. First, FGP outperforms the baseline pre-training methods in 23 out of 27 settings. Second, our flow surrogate can effectively discriminate high and low performing architectures in the representation space, suggesting its effectiveness as the pre-training method for neural architecture encoding. Let me wrap up my presentation. We aim to train an architecture encoder that captures key characteristics of architectures. To this end, we propose FGP, a generative pre-training method that helps the encoder to capture an architecture's information flow. We show that FGP outperforms the baseline methods on performance prediction. Thank you for listening.